Hey, welcome back. It's time to talk about some of the most fundamental pieces of modern AI tech. Underpins so much of what exists these days, especially as AI continues to rocket off. And it's the core concept of what are neural networks even about? How are they built, and how do they fit into our approach of modeling phenomena that exist in humans? A lot to get through, so let's just start moving. Can I click yes? There we go. First, I'm going to shock you. A brain. It's a medical. This is a brain. It's still enclosed in its sac. It's a thing that you have. It protects your brain. So this is functionally your wire network. You have one of these in your head, so get comfortable with it. It looks like a big, blob of mashed potatoes when you just look at it. But remember, you are cells. You are entirely made up of cells, and the cells contained in this are a special form of cell, a neuron. Now, you're not trying to memorize all of this, but this is a fairly accurate depiction, at least on the right side here, of a single type of neuron. We'll continue on talking about the bodily shapes and stuff in a moment. There are a variety of cells, right? There's a whole bunch of different ways that neurons have their dendrites and axons. So dendrites are the parts that detect information, and axons, the axon nodes, are the ones that send information. And this is a fairly decent depiction of one. Let's keep going and get a little more abstract, right? Remember, abstractions, we are modeling, we are trying to get the concepts down, which is also where this begins. So, how on earth does a blob of mashed potatoes transmit information? Also known as a brain. Okay, so there's three major components. Again, we're already kind of boiling things down. The dendrites are the first part of the information transmission process, right? So this is a single cell. This is a cell like a cell body, like anywhere else in your body or in any other animal. It's just a really special kind of cell that reacts strangely to things around it. So dendrites will detect signals from other cells. What they do is neurotransmitters are ejected from other neurons, and this cell catches them. Those transmitters trigger this cell, the one that we are, to let more or fewer ions from the surrounding sort of fluid ecosystem of the your nervous system, including inside your brain, to let different amounts of ions come into the cell. So in the cell body, you develop a charge based on how many of these ions are in there, right? So if I have a lot of negative ions in my cell, I become negatively charged. So once the charge reaches a certain threshold, so it becomes charged enough, and I always forget if it's typically labeled as positive or negative, but the point is more about a difference, right? So if it leans too far in one direction, what you trigger is called an action potential, where this irreversible cascade travels down the axon, right? And what does it mean, travels? Similar thing. More ions are let in all along the axon. It's just done in a way that is forced. The ion charges flood the system, boom, 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 until we get to the end, at which point, and I use the thought here, like dominoes falling. So at the end, axon terminals, this is where, if a charge has come towards the axon terminals, now these will emit neurotransmitters ready to be caught by the next neuron, or next tons of neurons. It can be many to many, many to one to one, lots of ways to arrange neural cells. So that is a very short version of the biology. But it's enough, I think, to get a grasp of, okay, so we've just explained how a cell can manipulate its own ionic charges. not manipulate, but like it, how its body reacts to the ionic charges around it, and how you can trigger a bit of information, which is this guy was active, to go boop 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 and make the next guy active. That's information, baby. Now, a quick aside, I think a common question that comes up that maybe it doesn't even form in your head as a question. You're just sort of like, okay, I guess I get how they can send information around. But it's a bit circular, right? I just described how a neuron receives information from other neurons so that it can send information to other neurons. I think in a very abstract way that makes sense, but let's ground it, right? The grounding problem in a different, writ small. So we have two other types of systems or neurons, sensors. Sensory neurons, like, for example, feeling pressure, right? Touch your face or something of you. Touch it, press it right now. You feel it, right? The information gets to your brain. That is you having a sensation because something was smooshed your face. So what actually happens is similar to what we just talked about with the other neurons. A physical disturbance in the cell can cause it to sort of deform. So like, imagine the cell wall is stretching, because it is, and that might let more ions in. And once the ions are in, this cell can do the same thing we just talked about, send the message on through neurotransmitters to other neurons. So that's how we get into neuron space, right? This is the pressure to neural impulse transform. Then we also have motor neurons. This is how things get out of neuron space. So you have muscle fibers, and when they receive neurotransmitters from other neurons, just like we saw in the first neurons, not just the fibers. There's muscle cell. There are neural cells attached to the muscle fibers. When the muscle fibers receive these potentiations, they will then contract. That's just how they work, right? Give them the right charge, and they start their own little cascades of, I should shorten, and that's how you get a flex, right? This muscle blob gets a bunch of signals from my brain that say, oh, I guess it's time for us to shorten, and bop, here it comes, right? And that's how we get from neural impulse world to movement in the world. I'm having a phlegm moment. Hang on. All right, annoying. So this is the concept. This is the space we're in. This is how generally information gets into our system. It moves around in our system, and then it sometimes comes out of our system. So this is the car. Yeah. I just sketched this. So it's a broad sketch of how it all works, right? The world impacts certain sensory neurons with like pressure or light or chemical senses. Those get transformed almost immediately into neural impulses, right? So we get them right into information world, neural information world. And it can't be understated just how many synapses are in your nervous system, especially in the brain. The synapses are the connections between nodes in the brain. The connection from one neuron to another neuron, the gap there is the synaptic cleft, where neurotransmitters will go from one to another. Huge number of connections in your brain. It's thought that there's more connections in your brain than there are stars in the observable universe. And then the final thing is sometimes internal activity can cause changes in the brain itself. Oh, sorry, not final thing. This is an important sub-bullet. I just framed it as like information come in, information do thing, information go out. Another thing that can happen is that the information can just change the connections in your brain, right? That's what we call learning. So you're doing right now. You're trying to form new connections based on the inputs and sensory details you are receiving. You aren't necessarily moving so much, but it is still having an effect on your system. And then finally, not always, but often, the impulses result in some kind of motor action, like talking or moving your arms around. So, this little cell is pretty cool. It's able to achieve quite a lot thanks to its ability to transmit information. It's a core function of our whole system, right? I wonder if we can model that. So, here, let's talk about the simplifications involved. We have our dendrites, we have our cell bodies, the nucleus is neither here nor there, and then the axon and the axon terminals, right? There are three major informational structures here. Dendrites that make up the input, cell body, which makes up sort of the decision, are we going to transform or not, and the output. Am I sending something or am I not sending something? The simplification is, we could imagine this if we're just going to stick to binary, which is a good way to start. I'm either getting a signal or I'm not, and I'm either sending a signal or I'm not. How can we do this a little bit mathy? Well, if, let's say, the input information, let's say there's 4 connections coming in from outside, from other neurons, and they're all giving 1s or 0s. Okay, so I'm getting 1 from A, 0 from B, 1 from C, 0 from D. The cell body now is this decision system where we're asking, okay, should I, let me sum up all the information that has come in and decide whether or not to fire based on how strongly activated I am. Are you getting the picture? And then output bit would be either I did or did not fire. Okay. So, look what we just did. We've just kind of invented the perceptron. This was the point. Showing that by doing a little bit of a sketch of an informational sketch of how information moves in neural spaces like this, we've kind of backed into the perceptron model. So the whole idea is that if neurons are clearly capable of a lot, they can say words at you like this right now, right? They can be in the world, they can move you into and out of any situation you've ever been in. And obviously we know that they are very complex. We started with that. They are more complex than we have understanding of. But even if we can't model that full complexity, right? Modeling is inherently reductive. The question is, can we get some, like this was the motivation for building the perceptron model, is originally back in the, was it 70s? Anyway, I should have had a citation here. But where does this get us, right? If I'm able to do this little, like, okay, well, here's a single node and how it moves information. Does that take us, how far can we get, right? And can we get a system that starts to simulate some of the power of our systems, right? The answer is, of course we can. This is how it all works now in AI Town. But let's start with the first step, right? So the idea is, like, where can we get with this? The first step is, okay, let's actually build it. And we're modeling a single neuron simplest type of processing, fire or don't, based on inputs. So, getting a little bit mathy, we don't need to belabor this. I think I'll just gloss over this one. As in, it's here for reference, but here's the deal. Information is going to come in from somewhere, either other perceptrons or the outside world. Maybe I'm trying to do a picture of, take inputs as like the light from a pixel cell of a photo or something, right? But whatever it is, it's some kind of input number, and usually it's a 1 or a 0. These are all weighted. This is key. They have a weight value. Weights can be changed to update how this thing should integrate all the information coming into it. And then, don't run off. This sigma thing just means sum this shit all up, which says add together all of these, like, so this input might be a 1 and it's being multiplied by like 0.1. It's not a very strong connection. This one might be being multiplied by 50. It's a very strong connection. This one might be being multiplied by -2, right? So all the different connections coming into this neuron, this neural cell, are being summed up based on how strong the connection is between this cell and the previous cell. And then finally, the question is, do I reach threshold? After summing up all the values of this, do I reach a point where I'm going to fire? And the firing is, once again, just a 1 or a 0 as we receive for input. So, cool. We just described all the math. What does this buy us? Why is this useful? And like, what does this even get us? A single one of these get us? And the answer is some basic Boolean functions. I don't want to belabor this too long, but let's highlight the basic concepts. For and, you would need to do so and, right? For and to be true, both inputs must be true. If one is not true, then I can't fire, right? This is classic like truth table stuff. You know what? I'll go forward, but then we'll come back to this one. The truth table for and, right, is if both inputs must be true. The truth table for or would say either of the inputs can be true, right? I can have either just the one on the first value or the second value or both. Any of them is fine. And then finally not, you don't even need two inputs for not, it's just an inversion. So how are we doing this? Here are the key features, right? We already know that inputs come in as a 1 or a 0 and that they are weighted somehow, and then the threshold, T represented here, is set, and then we decide whether or not to fire based on the sum. For and, oh no, I lost my and symbol. Okay, that's fine. So for and, the threshold is set high. The weights are set, just fine. You can leave them at 1 and 1. And if the threshold is high enough, you'll need both weights to get summed enough to cross the threshold and output. Yeah? Or is the same way, it's just the threshold is set lower so that even that 1 can be output. So rather, either of these inputs can be active, and then the output will still fire, right? Satisfying our truth table. And then finally, in this one, it doesn't matter too much about the threshold. I mean, it needs to be set near 0. But in this one, the weight is actually negative, meaning that the input from outside this cell is going to negatively impact. It's going to suppress the activity of this cell. And you do that in the right combination here of a strong negative weight with a threshold near 0, and it's able to invert the signal. If a 0 comes in, it's staying above the little slightly negative threshold, so we output a positive. We output a 1. If a 1 comes in, we multiply by -1, we go way below threshold, we don't output. This is a pretty powerful set of basic Boolean logic, and we can do it just by twisting the knobs on what exists here. I'm going to come back to that twisting the knobs concept. You can do it all manually like this, right? So you can say, oh, I found the right threshold. I found the right weightings to make it so that one node is able to do this basic logical process. And that's actually great. Now, a quick aside, a question is, how real is this, right? I've already set the stage that you know that perceptrons are not real. They are a first step at modeling how this information moves. But I just wanted to illustrate for you, in reality, neurons are actually firing in real time, right? It's not just a single boop and then something, you move on with your day. Oh, I got the 1 or the 0. It's always producing patterns of outputs. So here's a little what am I calling this? A visualization, a figure from an interactive figure, or rather animated figure from this site here. This is so in this little study, they would just stimulate the neuron with an electrode, right? Kind of fake the ion stuff to see at what point does it start firing. And this first one is saying, okay, we're going to stimulate with like a really, really light amount of signal. Doesn't get much electricity at all. And you see that not much happens, right? If you give it a little bit, well, it's able to fire, and then it takes a minute and it rebuilds, and then it might fire again. Give it a strong signal, fire, 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 fire. Give it a really strong signal, fire, 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 fire. You're seeing what I mean, that a single neuron can represent more than just a binary 1 or 0. All of this, by the way, is why Spawn is so interesting, is that it does model this. It uses real-time simulations of neurons as opposed to just this sort of simplification, right? But it's also way more computationally expensive and stuff. So the real question, back to our core tenet in this course, is modeling the time-frozen, binary, simplified version of a neuron useful? And the answer is, God, yes. So let's get back to this concept. So we're trying to move... We concede that at least and or a not are possible to recreate in a single perceptron, right? And if you know anything about computing, you know that's actually awesome. You are well on your way to being a Turing-complete computing system with just those three. Not quite there, but you are getting there. Wait, maybe you are. Well, anyway, point is, the functions alone are not very interesting, right? I combined 2 bits and I changed into a different bit. Oh, that's fine, right? The real power is that you can combine them. So, you know, there's other simple Boolean functions that exist, right? Exclusive OR is one that we use all the time. In fact, whenever you say OR in English language, you tend to be using sort of the forced choice thing. It's true only if one or the other is true. I'm not going to do both, right? So a single perceptron can't handle that. The reason is it can only handle functions that are linearly separable. And what does that mean? Well, it's a fancy way of saying I can't do this with a single cutoff value. I need multiple knobs to tweak to make this possible. And you can sort of see it here. The way we were doing things before, input 1 is on the x-axis, input 2 is on the y-axis. So when they were both 0, easy. 1, 1, only true when and is here. We're drawing one line through that space. We're drawing one line through the OR space. When you get to XOR, you need more than one line, right? You need more than one simple cutoff value. So this is the power. This is going to illustrate for you how you get from a single, simple, fake neuron to something more complex. So let's try to walk through XOR. Okay, XOR truth table here. It's not going to be true when... Here, we'll do the simplest. I want to do this... I want it to be true that any of the choices are good, but also not both. Now, any implies an OR operation, not implies a NOT operation, and both implies an AND operation. Guess what we're going to do? So you connect them all up together. You have your 2 inputs, and this looks a little complex, but really what all this means is each input is being fed to both of these nodes. There's an AND and an OR. And the concept is, so this is literally just an AND like we described it before. It's saying, I have a high threshold and I will activate when ready. This one says, I have a low threshold and I will activate when ready. And, you know, they produce the AND truth table and the OR truth table. Now, we have the OR, we want to carry that through, so we just give it the same weight. Like, okay, if the 1's come out of here, send the 1 on. But this one is going to compete. And it's going to say, if both are true, actually negate the signal, convert it back to nothing. This one will only be lit up when both are true, and then we use it to negate the output. You see what I'm saying? So we're doing a not on this AND. We're saying, not both. Anything's cool, but not when both are present. And then our output becomes this appropriate truth table. If you want to stop and study this, you can, of course. But I'm showing my work. But it's still... so let's keep moving. There's plenty of stuff in this one. So here's an interesting little tidbit. Well, we're going to flash forward to this. We've just made our first feed-forward network. Artificial neural networks. Oh ho. Interesting topics there. So this is an example of how you combine simple computing units, combine them in a particular way, with particular weights and particular thresholds and particular values, and we get a more complex function simulated. It can continue to scale And that's where we get into the concept of connectionism as networks of nodes working together to compute and do things. So perceptrons are little artificial neurons that simulate the bare minimum, right? 1-bit processing. You can hook them up together, so you can say or and not or plus not and is XOR, sort of, is what we just illustrated. Not in a very mathy way. And then you can just continue to do that. You can hook up more and more. You can hook up many, many bits of these perceptrons together in a complex network to really, really start to do large-scale things like we've begun to see now. And this is all the underpinnings of connectionism. This is the notion that the most critical aspect of understanding these types of complex information transformations, like in brains, is to model the connections. The shapes these connections take in these networks, in the form of different types of neural networks, define what they can do. In general, just like with brains, they have some kind of input. You know, maybe it's 1, maybe it's 12, maybe it's 1,000,000, but either way, there is some way information is getting into neural space. And then there has to be some kind of output where information is leaving neural space, just like with our sensory neurons and our motor neurons, right? And another bit, though, is that they often have hidden layers. This is the stuff that's happening between input and output in the weird, interesting spaces. These are deeper nodes that exist only to support the transmission and transformation of information from one end to the other. These are actually super critical. They're the most interesting, and there's a lot to them. We won't stick forever, but let's keep going. So let's describe some of these shapes that neural networks can take when you start to staple them together like this. One important aspect is flow. Feed-forward networks are the kind that nodes from one layer, they connect only forward. They only move in the direction of, they don't like double back, right? So once one layer is done computing whatever it's doing, once those nodes are active, they just send information on, and there's no sort of redundancy. It's very straightforward. This is like the standard way that people do things. In fact, even the biggest stuff you're seeing today are mostly feed-forward networks. Recurrent networks, though, these allow nodes to reconnect to themselves, and they allow for sort of like looping of information, also known as memory. Retaining information from one execution to another, a loop that keeps something active, like say when you are rehearsing a phone number before you write it down, right? You are keeping the information active. Even if you're not saying it, you can use internal systems to loop and keep information active until you're done. So, totally mutually exclusive from feed forward. These are different types of networks. And it can offer struggles in understanding what exactly is going on when you're building them. Sometimes it adds complexity because now you have like ghost signals in the network, but very powerful. And some think the next big leap in AI might come when we get these things working at scale instead of the feed-forward type. We'll see. Okay, now I'm broadly calling this one shape. Convolutional neural networks, they're typically used for like two-dimensional grid-like data, like say images, like this video, right? It's a grid of light, tiny pixels that are all arranged like this. And the main idea here is that because you are actually treating them not just as like a big line of totally separate, unrelated inputs, in fact, you might arrange the connections so that this one will be connected to this node, and then also all the ones around it will be connected to this node. This is where we get into simulating things like your eyeball, your retina, right? Your retina is a pattern of spatially connected neural inputs, and it doesn't just get turned into a line and sent off to information space in the brain. You can do things with, oh, this one nearby has it's dark, but then all of its neighbors are light, a center surround. Interesting. It makes them very useful for processing information like this, right? Two-dimensional information has useful patterns in it, So why not build networks that are focused on looking at those patterns, those spatial patterns? Then we get to deep learning networks, and this is where all those hidden layers come in. Lots and lots of hidden layers, in fact. And this is what allows for huge levels of abstraction and powerful forms of inference in the models. This is all the modern AI stuff you're seeing lately is deep in this way. Now, why are deep networks tricky? Well, because the deeper the node is into the network, the farther away it is from the input and also the output, which we'll see in a minute when we talk about learning, the harder it is to train it. You know, it needs a lot of data and a lot of training time to, you know, push the signal in and get these middle nodes to start doing things that you want them to do. It's almost like having a whole lot of information inputs is a tricky thing, and it takes many years for a human to get to a place where it makes sense. This is why getting information into systems that are deep it's a long process, effortful even. Okay, and now let's talk about transformations. This is sort of back to the idea of like, okay, what is the whole system doing, right? What's the goal of the network? And we'll talk about two right now. Many to one would be the idea of I have lots and lots of inputs, but I'm only going to really output one lit up specific node. And what is this like? So here we have the example of the cat image and the dog image. These go into a convolutional network, right? So it's going to use the spatial information in the images, and they get parsed into smaller and smaller feature detector abstractions until you get to a final array of just one node hooked up to all the things that came before it, but it's a lot of nodes. In this array, you might have a cat node and a dog node. And given both of these images, both of those outputs might light up a little bit, but one is going to be a lot stronger, right? One is going to be stronger than all the rest, and that's when we say we have taken the inputs of many and smoosh them down into one choice, which is, I think this is a cat, right? I show you a picture of cat, and at some point it becomes a symbol, a singular label, a singular point that you're able to use and say, cat. I understand cat. I think this is a cat, right? This idea of getting into symbols. So both nodes, many nodes might light up, but one will be strongest. So this is the idea of a classifier. You're taking lots of information and you're trying to boil it down into a point, a single point. Semantic pointer, like in Spawn. Then we have many to many, which is more of the modern stuff we've been seeing lately. Some sequence of lots of stuff turns into some other sequence of lots of stuff, right? Taking some group of inputs, like an image or a series of words, and using that to produce some other output that is also a series of, like an image, lots of pixels, or output of words, right? So you may have seen many of these things lately. Text to image would be things like Midjourney and DALL-E, where you write a prompt, many, right? Lots of text, and then out comes an array of pixels that is a picture. Image to text, so things like the Be My Eyes scene describer will take a bunch of pixels and then turn that into an output sequence of text, right? Text to text, so like chatbots like GPT, you give it a prompt, it gives you an output of text, right? Or in this example down here, translators, right? Automatic translation tools are many to many. They are a sequence of one language, goes into a bunch of networks and gets all chopped and smushed, moved around, and then it gets translated out to a different language. So, yes, that's a lot of ways to connect nodes together. We've just kind of gleaned the surface area of neural network structures. But we're left with a sort of a conundrum, right? Because we saw how building just one extremely tiny network of 3 nodes by hand, I say it's a pain here. I didn't it didn't feel like a pain, I don't think, when we talked about it. But you could imagine if you just had to sit there and like tweak thresholds and weights of 5, 10, 20 guys until you get the right output, that's going to waste your entire life, right? Especially when we get to a point where we have networks that have a number of weights that are in the billions, right? So this is where machine learning comes in, to let us build and tune networks autonomously using data rather than trying to do anything like this by hand. So we're in phase 3 of the lecture. Let's talk about learning mechanisms. So back to our Perceptron friend. We've heard, everyone I think has heard the words machine learning before, and it's been applied in many ways, but here we can kind of point directly at the math, and I'm going to walk you through some basic concepts for it. We can algorithmically, these are the machine learning algorithms, adjust weights and biases. So bias is a new term, essentially the inverse of the threshold, right? If the bias is high, that means it's easy to fire. Typically, you leave the threshold at a single value, and instead you just introduce a bias value. Point is, it's one of two things, right? So, let's see. Oh, right. So we can adjust these things continuously using training, right? Doing a training algorithm. And what the point of it is to tune the connections between groups of nodes and within groups of nodes. I'm calling nodes like that. A single node would be a perceptron. There's other kinds of nodes now, slightly different tweaks, different activation functions and stuff. So that given a particular input on one end of the network, like we've been talking about, it can produce some desired output, like the cat image, right? If you show a naive network a photo of a cat, it'll just randomly spit out one of its possible labels. It might say that's a hammer, just because it would have a random understanding of the world. The goal is to make it so that you train it so that cat will activate the node cat, right? So there's two primary forms of learning mechanisms, training mechanisms. There's supervised learning and there's unsupervised learning. In unsupervised learning, there is no goal, right? You are just shoving information into the network and you're saying, hey, eat this, pick up patterns, I don't know, just see how things move together in the world. I show you 7 million photos of a cat. You will start to recognize the cat even if you don't know what it's called, right? So that pattern will make sense. You would be able to say, oh, I see ears poking over that fence. That thing might be over there, right? So you're getting the sort of the bottom up, just absorb patterns from the world. Then there's supervised learning, which is there is some goal, and if the system produces the correct output during this training, you increase the weights that fired. If the system produces the wrong thing, you decrease the weights that fired. You say, you have done wrong, I will punish. Don't worry, they don't feel anything, they're nodes. But you have supervised, so you have this unsupervised and supervised learning. Both are super useful, and they're used in different ways, and it's mostly about, what it comes down to is the selection process of how you determine which weights to update and by how much. So, let's get into unsupervised learning. And we're going to do a little walkthrough to explain how exactly this works in sort of an intuitive way, I hope. So, unsupervised learning, Hebbian learning, you might hear that called before. Hebbian learning is neurons that fire together, wire together. This is good. This is like an accurate depiction of certain types of learning in the brain. So the idea is, given a network, tiny little network, in this case we have 4 input nodes and 1 output node. We're trying essentially a perceptron, but we're treating them as separate nodes, right? So when a node in the network fires, other nodes that fired that same iteration will have their connections strengthened, okay? So it's like the idea of trying to imprint a pattern onto the network, like I was talking about with the cat, right? So the basics of how this works is, let's say we have an input network. We have 4 input nodes. Sorry, not input, a network at all. We have 4 input nodes connected to 1 output node, and the weights between them start kind of really close to 0. But what you do is you set the bias of the output node fairly high so that it's easy to push it over the threshold and fire. And there's a little bit of noise in the system too. You want this during training so that it doesn't get fully stuck. I mean, if you didn't have the bias set right, it might never be able to it might never be able to produce a firing pattern at all if there's not a little bit of noise making it, oops, on occasion it might fire off. So, if you want to know more about that, talk to a robot. Let's walk through this process. How does this actually work at this level of a simple network? So, let's say you push a pattern of inputs into it once. Let's say 1 0 1 0. The first node and the third node are going to fire off, right? Initially, like we were talking about a moment ago, maybe nothing happens. Maybe the node stays dark just because the output node doesn't light up. It doesn't decide to fire because, it was randomly just not right the first time. It's like applying to grad school, right? But the next time, the noise might just arrange just right that this random kind of pattern that the network doesn't know anything about actually does produce a firing. The output node does light up. So in this case, in this scenario, now that we've had some firing patterns, so like these weights manage to push the threshold over and allow a firing to happen. So now the first and those third nodes, because they fired when the output node fired, Hebbian learning comes in and says, hey, that must be a pattern. And it strengthens the weights between those two and the output. And it increases the weight. So you keep doing this. Now it's even easier to get this pattern to fire on the node. And ultimately we get to a point where, aha, we have created a classifier for 1010. This is a stupid simple pattern, but we've made it so that this output node has sort of picked up on the fact that this is a distinct pattern that it should light up for. And so, to illustrate this a little better visually, I would have interleaved these together, but Google Slides doesn't allow you to do that. Infuriating. So, first try, nothing happens, right? These two have lit up, these two have stayed dark, so 1 0 1 0, and the output doesn't happen. Second try, we start to get somewhere. So we actually do the same kind of thing, and then the pattern lights up. So these two connections get a little bit strengthened, just a bit, right? And we keep going. Each time this output pattern lights up from this input pattern, output node lights up from this input pattern, it gets stronger and stronger until now we have a clean little classifier. This classifier is designed to detect 1010. That specific pattern. Zoom out, and we get to, that's how we can have the cat detector, right? You have a node system that is pushed a bunch of information in over and over and over and over, abstract features, many layers, until finally it's able to say, oh, so this shape with these funny little triangles on the top, I think that's a cat, just based on the many, many layers of abstract these going on throughout. These would get pushed into a feature detector that might be combined with other features into another feature detector, with other features into another feature detector, until you get to, I think this whole ass image is a cat. Now let's talk about backpropagation and gradient descent. So supervised learning. This is the case where your data has a set of correct answers, right? Over here on the right side, we see in the same kind of space as what we were just doing with the Hebbian stuff is, I see, so the correct answer for 1 0 1 0 is for the output node to fire. All other combinations of patterns, the output node should not fire, right? So, what do we do with that? Well, the answer is a complex process of assigning blame and updating values. So when you put the input in, you can compute what's called an error signal, because you know the output you want. If I put in a 1 and if I put in a pattern and I'm expecting a 1 because I'm expecting, hey, this is the right pattern, and it gives me a 0, that's a very strong error signal. That is I was off by an entire whole value of whatever. So it's essentially a way of saying, how wrong was I? We're keeping it simple in the simple case because, again, we're working with perceptrons that just do 1s, 0s to 1s, 0s. Again, there's other ways of doing this, but in the case of the simple 1 or 0, it can either be not really wrong at all or extremely wrong. It can be, hey, I got it right, versus I got it very unright, totally not right at all. Backpropagation is the first step. It kicks in and says, okay, for each weight, I'm going to go calculate how much a change in that weight would impact the output error. So it goes into the connection between A and X, and it says, hey, were you responsible for this error, and by how much and in what direction? And it goes to B, were you responsible for this error, and how much and in what direction? And does it for all of the weights in the network. That's why it's expensive. Think about training a 175 billion node network. So for each weight, it calculates how much it's involved, right? And what direction it's wrong in. This is where gradient descent comes in, a very fancy way of saying, nudge it the right direction then. So if we know what direction it's wrong in, nudge it back. Nudge it the other way. So the idea is to try and continuously training on this training data to make it so that it gets the error signal very, very low or non-existent. It's trying to say, get rid of this error. Continue to I'm going to keep adjusting the weights until we get a pattern that until you light up when I say you should light up and you don't light up when I say you shouldn't light up. Same deal. We're trying to build the classifier, but we're just doing it with training data instead. It's costly. It involves looking at all the weights many times, but it results in the very specifically shaped training of the model, and it can be extremely good at imparting specific things into the model, specific shapes, not just generally observed shapes from the Hebbian learning, the fire together, wire together side, but specific things that you know you want. So let's do another walkthrough, similar. So we're pushing 1010 into the network again, the same little network. You know what, I'm just going to get the whole thing up there because I think the visuals are useful. We push 1010 into the network. This time, we know the correct output should be a 1. Initially, let's say the output node returns a 0. It outputs nothing. Which would make sense if it was a dumb network that hadn't been trained at all, because it would be like, I don't know what that is, I'm just going to say 0. So, because 0 is sort of default. Its error signal would be huge, right? Its error signal will be a whole 1.0. So now backpropagation comes in and says, whoa, we got a big error signal. It's going to go look at, hey, who was involved? Who fired during this one? Well, we know in 1010, A fired and C fired. And produced basically the nil output. And the idea here is we see, okay, so these were way off, and they were way off in the specific direction. Gradient descent comes in and says, okay, I'm going to nudge these weights up, because obviously the weights aren't strong enough to produce the desired output on these nodes. So, and we got to push them up a lot, because those weights really weren't pulling their own weight. Repeat this process of, I say ad nauseum here, a lot, right? A lot. But gradually, the system, this process will turn those knobs over and over until, you know, it really strengthens them until we got, again, a similar kind of classifier. Now, would you use backprop and gradient descent or Hebbian learning for this? Depends on a lot of factors of like what you're trying to do at all. But overall, this is the vibe. This is the process. So, yeah, we have supervised and unsupervised learning. Let's talk about GPT, transformers. These are, we've talked about before, of course, but these are, let's use the terms we've learned today. Oops, I didn't know scroll up would move that. The terms we've learned today. Transformers are the chat GPT, right? Things that you can talk to. They do all this crazy stuff, and you're like, wow, it sure does talk words good. What is it? Now, the answer is, they've done a lot of architecting to add many subsystems with, like, this little classifier is just for this, and this thing is for encoding whole strings of blah, blah, blah. It's all networks still, but they're all getting kind of strung together. The main features are, it's a deep network, so it has tons and tons of hidden layers, lots of training going on. They are feed-forward networks, because recurrent networks they're harder to work with, and I think they're more expensive to train. There's a lot of ways things can go weird. So transformers are still the simple kind, the feed-forward only. Step 1 goes to step 2, goes to step 3, until we get a token out the other side. Classifiers are involved, for sure, because think about, we've discussed this before, GPT produces one token at a time. It takes your big blob of words and it says, I think that you are cool, or whatever it's going to say to you. If you begged it to call you cool, it would do that. And it's producing one at a time, right? That specific step is a classifier. It did all this work from the input text through lots of coding, through all the language stuff it has built into it, blah, 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 but the output is one of the many possible tokens that it knows. It might be a word, it might be a symbol, but either way, one, right? Many to one. But ultimately, we would call this a sequence-to-sequence system, because you're not done with one token. The whole point of it is to produce lots of tokens until you have a sequence. So, this system is a sequence-to-sequence, feed-forward deep learning network that involves classifiers to some extent. And talking about their training, so thinking about what we just learned about backpropagation and gradient descent and Hebbian learning. So there are two phases to training a transformer model. There's the base model, where you are just exposing it to language as much as you can find. All the language in the data set, there is no goal. You are just shoving sequences of language into the system, and it will bind itself. It will adjust its weights as patterns are fired together. Those patterns keep firing together, right? Fire together, wire together. This is how the base model of all large language models functions. It is just a slab of raw language. Fine-tuning is where you come in and say, there are certain parts of this slab that are more desirable. Like, I think we talked about this before, but GPT is fine-tuned towards the chat pattern. Meaning, if I type a bunch of words and I ask a question, don't just then list 75 new questions, because you've seen before in the language that exists that after a question comes more questions, right? Like a review pamphlet or something for a course. Fine-tuning says, no, you stop producing questions. You produce a question, kill those weights, kill those weights, kill those weights, kill those weights, until finally you get to a point where, even though it has contained in it a huge amount of the language in the universe, it's more likely to guide itself towards your goal language patterns, which are things like responding in a conversational tone, answering questions when they are asked, that kind of stuff. That's how the fine-tuning works with something like GPT. Requires tons and tons and tons and tons of data. It's a heavy-duty lift. There's a reason this corporation has control of it, and it's not in our houses yet. One day maybe. But I didn't note it here, but another good thing now that you will understand is, whenever you see the word parameters when talking about models, so the GPT 3.5 has 175 billion parameters. GPT 3 had 10 billion, or 2 had 10 billion parameters. There are local language models out there now that you can get that are 7 billion parameters, so 7 gigabytes worth. What does parameters mean? Parameters means the weights. The thing that we just spent all this time talking about setting, they're just numbers, right? They're just knobs. GPT 3.5 has 175 billion knobs, and they are all set to very specific weights. That's all it is. Not literally, obviously you can see here there's like subsections and pieces that fit into other pieces, but overall, it's just a boatload of knobs. So, that's it. Recapping. Whew, we came a long way in an hour. We saw how biological neurons function and to transmit information, and the basics of that is the dendrites build charge in the cell body, and that transmits information down the axon, which is then sent on to other information getters. Sensory cells can get information from outside into the system. Motor cells can get information from inside the system out into the world by like flexing an arm, etc. We showed how we showed how we model that process. I was like, model that with perceptrons, which we've simplified into their inputs, binary, weights, thresholds for firing / bias in other models, and outputs, 1 or 0 again. This is a simplified representation of neural information transmission. It's capable of, at base, using just some weights and thresholds and biases, and, or, and not, and then when we start stringing them together, we can get more complex things like XOR, or maybe like GPT or something, right? So that takes us to, we can connect individual nodes into networks of nodes. So these emerge from like connecting the dots between all of our nodes. We have different kinds of flow. There's feed-forward networks, recurrent networks. There's different shapes. There's convolutional 2D networks. There's deep networks that are very, very deep, very long. And different kinds of transformations, like classifiers that take lots of information and give us one symbol, or sequence to sequence, which is take one kind of information and turn it into a different kind of information. One large set of information, new large set of information. And because we don't want to do any of this by hand, we couldn't. It would take an eternity and no one would do it. You can train the networks algorithmically. So Hebbian learning is unsupervised, and it's this idea that the nodes that do fire together will start to wire up together. And then backpropagation and gradient descent is supervised, which is saying, I know the correct answers. I'm going to use error signals of your outputs to go back and adjust the weights that were involved in making the error. GPT is firmly rooted in all of this. I hope this is the strongest explainer so far for the underpinnings of how these things are structured. Because it's a combination of many of these basic features just at an incredible scale. Again, I think GPT-4 has something like 1 trillion parameters. It's a lot. It's a lot of nodes. It's a lot of knobs to be twisting. And that's it. Okay? Great. Thanks, and take care.